So after a lot of work and a lot of finagling, I ended up with this giant contraption you see here, which I'll explain in a minute. First, I'll introduce my lovely assistant, Sammy. She's my little girl. There she is. She's going to be changing the value in this measurement point A, which you see I've got my standard meter hooked up to. So when she increases the value, go ahead, put something in there. When she increases that value, pistons will automatically go up. And when she decreases it, it'll automatically go back down. So this right here is the device I use to transmit, and it's huge. And it's unfortunately huge, but it's pretty straightforward in design. Up here I have my variable potentiometer underneath. It's built exactly like the original. Then I transmit the signal from that variable potentiometer all the way back using a little series of comparators and input it into what you'll recognize as the large signal comparer. And then I take that signal comparer and compare it to the value of this hopper. And so the signal comparer, if it finds that the black hoppers is stronger, will say we need to increase the signal that's stored. So it'll send a pulse out here. And if it says, oh, the signal in the hopper is weaker, it'll send a pulse out here. And if they're equal, like they are right now, it won't send any pulses at all. Now the problem I had was this comparator works on 2 ticks. It brings the signal in 1 tick and sends out a signal in 2 ticks. And it takes 1, 2, 3, a whole bunch of ticks for the signal to get transmitted back. It takes a whole bunch of ticks for the signal to percolate through here. And no matter what I did, I ended up with my currently stored value, which is what this array is. This is to show me my currently stored value. It would go crazy with half values. Sometimes I'd be alternating between a value of 3 and a value of 10. Crazy stuff. You'll remember I showed you in the earlier video how this memory device, if you don't give it a good solid 10-tick pulse, can have a problem. So I built a 10-tick clock. That's all that is. And what that says is whatever the incoming value is, lock it down for 10 ticks. So if my comparator has said increase the value, then this will turn on, and this will lock it down for 10 ticks, and it keeps that memory device stable. And the same exact thing's going on over here. It's the same exact pulse, locking it down for 10 ticks. And so when Sammy puts, say, 1 or 2, stacks in there, then the memory device gets a tick, and you see the increased pulse is going, and then when she takes it back out again, a short pulse goes out, and the value goes down by 1. The trouble I had was that the time delay through all of this was even more than 10 ticks because it took some time to send it back and process it. And so what would happen is it would update and update and update, and it would just hold on to its update just a little too long. So back here I have a clock circuit set to 20 ticks, and you'll notice every time this flashes, every other time this flashes, you see. They're in sync. And so the comparator only gets to talk every 20 ticks or every 2 game seconds. And the memory updates for exactly 1 second or 10 ticks. And if it's got to increase, it sends a long pulse. If it has decreased, it sends a short pulse. So load it up, Sammy. Fill it right up.
My thing is glitching.
Nope, she's having technical difficulties.
I can't move.
There she goes.
I couldn't move.
Fill it right up. And you'll notice that immediately it starts sending every 2 seconds a long pulse to increase, a short pulse to decrease. Now if I fly way over here, we'll see that these pulses are being received, and this is slowly increasing. That's okay, Sammy. This is slowly increasing up to 15. And the nice thing about this compared to my first transmission method is that you notice these are unidirectional repeaters. And I don't have to push a button to get the new signal. As soon as the signal changes, I start getting updates about it. Sammy, empty it right out. As soon as she empties it out, I immediately start getting signals sent that say, oh, it's lower now, and it starts dropping down. The problem is that at a 2-second delay per signal transmission, it can take 30 seconds to go from an empty to a full state and a full to an empty state. Let's look briefly, though, at what's going on over here. Up here, I just have my variable potentiometer. That's all this is. It's got its clock sitting on top of it to regulate it to 10 seconds. And then I have a couple RS NOR latches. The RS NOR latches are very simple. When they get a pulse to increase, it sits here in the RS NOR latch, and then when the clock comes through and says, give me the value, which it does, the delay to the reset on the RS NOR latch lasts just a little bit longer. Fill it up again, Sammy. The delay on the RS NOR latch lasts just a little bit longer. It gets its signal transmitted, it locks it down, and then it resets it. And the same with the decrease. All these two things are signal measurers. This one says if the signal is long, it will last at least 4 ticks. If the signal is short, this is a short signal, and so if it's a short signal, it decreases it. So as the long ticks come through, you can see the RS NOR latch gets them, holds them, and transmits them on. And that's all there is to it. Go ahead and dump it out. The trouble is, like I say, the time it takes. And I'm thinking about all of these clocks I had to change. And I tried adjusting them all, and I tried shortening them and lengthening them. And this works, but it's quite a mess. And you'd have trouble building it from my video. Although if you put together all my videos, you could build it. But there it is. It's slowly decreasing. Oh, there we go. Visual glitch. Well, let's see what we did next. I'm going to take a little sidetrack here, but there we go. God, reset the time, and say goodbye, Sammy.
Oh, sorry, I didn't know Papa said. Where are you?
I'm behind you.
Oh.
Bye.
Bye, I mean.